Hi everyone, I'm Tim Hegeman. I'm from Delft University of Technology in the Netherlands, and I'm here on behalf of Alexandru Iosub, who is the task force leader for the graph analytics workload, also known as LDBC's Graphalytics. So the first question to answer would be, what's Graphalytics? So Graphalytics is a benchmark for graph analytics, and in fancy terms you could say that graph analytics consists of complex and holistic graph computations which may or may not be easily modeled as database queries, right? So they're not the typical short reads or the typical neighborhood explorations, but rather they're graph algorithms, and usually iterative graph algorithms. So why should we even care about these types of graph algorithms? Well, first of all, graph analytics is everywhere. It has many different applications, right? From identifying the key users in a social network to analyzing financial transactions and detecting fraud. It's useful for computer security, for example, to identify intrusions. So there's a lot of different applications, and many of these require the type of algorithms that you would not typically do in a graph database, but rather you would use something like a Pregel type of system, and usually also distributed systems, right? Because they're really large graphs, complex computations, heavy stuff. The second part of the motivation is that many of such graph analytic systems actually exist. In a survey we did a year or two ago, we found over 100 of these already out there. But comprehensive benchmarks for this space do not yet exist. There are some alternatives. For example, you could look at Graph 500, but most of these previous benchmarks focus either on one particular algorithm or one particular data set, rather than exploring really the space of graph analytics. So in Graphalytics we try to do things differently. So quick summary of the progress before I move into actually explaining what constitutes Graphalytics. So in the past 6 months and in the time before that, we've defined the benchmark elements. We've created a basic implementation of the tool chain, so a driver, but also tools to analyze results. And we have reference implementations ready for 6 different systems, including 3 implementations contributed by industry partners. And all of this has resulted in a VLDB article that will be presented, as Peter mentioned, later this year. And some of the partners in that collaboration are listed below. So in the remainder of this talk, I would like to share with you some of the details on the benchmark definition. I definitely won't have time to explain it all, but I'll certainly try to make a start. I'll be sharing a bit the tool chain that we have, what makes up the tool chain and its different components. I have one result just to give a glimpse of what comes out of this benchmark. Finally, some future plans and a conclusion. So, what makes up Graphalytics? In short, it's algorithms, it's data sets, and it's what we call experiments. And unlike something like a query-based benchmark, we do not have one particular workload that's comprised of a mix of different queries that then lead to a single score, but rather we have a bunch of different algorithms and a bunch of different data sets, and when combining that with particular setups of the system, so for example the number of machines or the number of threads used, and a number of metrics, we try to analyze particular features of a system, and I'll get back to what these features are, but think of something like the scalability of a system. So for the data sets and algorithms, to select the right ones to include in the benchmark, we used sort of a two-stage selection process with the goal of getting a representative set of algorithms and data sets, right? So as a user of this benchmark, you can feel confident that the results are actually representative for what you might expect under real use cases. But on the other hand, we also want to touch many different kinds of data sets or kinds of algorithms to make sure that we cover the different possible choke points of a system. So this is reflected in this two-stage selection process by first identifying the common classes of these data sets and algorithms, and then selecting from these classes sort of a couple of representatives that in the end make up a set that is diverse enough to touch all these different choke points. So we did this for the algorithms. We started out with doing surveys in 10 of the top conferences publishing on graph analytics. And we looked at what kinds of algorithms do they typically use to compare systems, right? So this includes publications on new graph analytic systems, it includes comparison studies, etc. And from these, we identified a number of key groups of algorithms, let's say, that we found were commonly used. And then from these groups, we selected a number of algorithms within the task force, right? So with consulting with both the industry partners and the members of the task force to make sure that we had a broad set of algorithms to cover the space. And I don't know if this is readable from the back, but we ended up with a short list of the different kinds of algorithms you might find on unweighted or weighted graphs, and then a couple of representatives. So for example, PageRank, BFS, weakly connected components, stuff like that. For the data sets, we use a very typical graph data model, right? So we just have a collection of vertices and edges. Edges may be directed or undirected. There may be properties. But one thing that's important about graphalytics and quite different from, for example, the SMB interactive workload is that graphalytics does not impose any kind of semantics on the data sets. So we're not just looking at social graphs, we're not looking at any particular kind of graph actually. As long as it's a graph and as long as it has the properties required to run, for example, single source shortest paths, then it can be included in the benchmark. And this feature is important because we try to really cover the space of graph analytics and not be too narrow on any particular application. So based on this, we selected 3 domains from which we took 6 real-world graphs, knowledge, social, and gaming domains, as they have quite different characteristics in terms of density, in terms of diameter, etc. And on top of that, we have included 2 synthetic dataset generators that allow us to test the scalability of a system, right? So we have these generators for which we can really generate small graphs up to very big graphs to test how the system behaves on the same type of graph with rather different sizes. And I'll get back to that shortly. So given these algorithms and data sets, we've devised 3 kinds of experiments, right? Experiments are targeted at really analyzing one particular property of a system. So the first group would be just baseline experiments, which simply run either 1 or 2 algorithms on a whole bunch of data sets to see how the data set influences the performance, or it might run on one particular data set a whole bunch of algorithms to see how the algorithm is impacted by the platform. And for this we measure both the make span, so the time from starting the algorithm until completion, but also the processing time, which is more of an internal property of a system, and the processing time in particular is from starting really the algorithm-specific code until the final results. So makespan includes also loading time, it includes storing the results, etc. Processing time is really purely given that the data set is ready. How long does it take to compute this particular algorithm? And it might give an indication in the future if you were to chain these algorithms one after the other. You would likely not have to repeatedly load the graph again and again. So processing time gives a bit of a better indication of what you could expect in real-world usage. The second kind of experiments are focused on the scalability of these systems, because graph analytics is typically done either on large parallel machines or on distributed machines. And for this we've included experiments for both horizontal and vertical scalability, so adding either resources in the form of more computers or adding resources in the form of bigger computers. And strong versus weak scalability. So either you add more resources but keep the workload the same and you hope to then decrease the processing time, or you keep the workload proportional to the size of your system, and then you of course hope that adding more machines means that this bigger workload still takes just as long, even though in practice that doesn't work. And the third and final component, which we believe is quite important, especially in the field of distributed systems, is that we look at the robustness of these systems. So for many of these systems, it's great if it works really fast on one particular graph and one particular algorithm, but if it completely breaks on another, then it's probably not going to be a wise choice. So what we look at is one, the limit of the system, so what is the smallest graph for which a particular algorithm is unable to complete. And on the other hand, we look at the performance variability, which is simply just repeating one particular algorithm and data set and seeing how constant the runtime is across these iterations. As with the SMB interactive benchmark, we also have an SLA that these systems need to abide by. It's quite simple. The output needs to be correct, which I think is a given. And the make span of any particular algorithm running on any data set is not allowed to exceed 1 hour. Now for our benchmark, if a system fails to uphold this SLA, it does not mean that it fails the entire benchmark, but rather that that particular experiment is not able to complete on this particular platform, which is a perfectly valid result. But it gives an indication of what are the limitations of any given system. 1 hour in this case is a bit of an arbitrary cutoff, but at some point you want your benchmark to actually complete. So we chose a bit on the short side. So for correctness of output, we have a validation process, which basically means that we have reference output for all the data sets and all the algorithms, even though something like local clustering coefficient took 2 weeks to run on the Twitter graph. We have all of that right now. And what we check for is that the output is equivalent. So it doesn't need to be byte for byte the same as what we produce, but rather, for example, for weakly connected components, we require that all the vertices in the same component are given the same label. What that label is doesn't really matter as long as it's the same. So in that sense, we still allow room for different implementations as long as they solve the same problem, let's say. And the final component of this benchmark definition is what we call the renewal process. And this was born from the observation that graph analytics is still very much an evolving field. We don't really know what's out there. We don't really know what are going to be the important algorithms even next year. So we've accounted for that by including in the benchmark a definition of how we are going to update in the future the workload of the benchmark. And in short, every X years, where X is probably going to be 1 or 2 years, something like that, we're going to repeat this two-stage selection process to identify the possibly new classes of algorithms or classes of data sets that are important, select new representatives. We'll be doing so in a way where across generations we're still able to compare, but let's say 2 generations from now, some of the algorithms we have now may have been dropped. But we try to do that gradually to ensure that we get a sort of a smooth process and we don't alienate, let's say, the user base of this benchmark. So what does it actually look like in terms of tools? The tools are online on the TU Delft GitHub repository. They will be moved to the LDBC repository probably in the near future, but they're already available if you want to have a look. So the architecture has updated a bit from the picture Peter included in his slides earlier. It's a bit too much to explain all of this, but there are some workloads there. So the data sets we provide, there's a system under test, which may be running on the cloud or in your own infrastructure. But there are 2 main parts of the architecture that are relevant. And at the core, it's the harness, the core harness, which is provided by us to issue instructions on how to run the benchmark. And there is a driver that's specific to a platform which can then take these instructions and actually execute algorithms. So this platform driver really only has 3 functions. You need to be able to upload the graph. So we provide a graph in a particular format, and we allow every platform to take this format, convert it to something that's specific to their system, or maybe insert it into a database, upload it to a distributed file system and whatnot. And this process is timed, but it's not included for any particular algorithm, right? This is just something you do once for a graph, and then you can run as many algorithms on it as you want. Which is also the second function. It needs to be able to execute an algorithm on a given graph. Easier said than done, because of course you also need to provide the actual implementation of the algorithm, but that would be the second function. And finally, if needed, you can delete the graph from your database to make sure that the next graph can be uploaded and we can continue. So what is the harness then responsible for? Well, it calls the upload, execute, and delete functions in a particular order to ensure that all the combinations needed for an experiment are all executed. So it basically does all of this bookkeeping and anything you expect from a typical workload driver. And as mentioned, the upload time is measured by the harness. The make span is measured as well. The processing time is something that must be reported by the specific platform, because it's an internal property of the system, and that must be exposed through its execution logs. And I'll get back to that in a second. So the second key part of the architecture is how the results of this benchmark are actually processed. So after running all these algorithms, you produce a lot of logs, a lot of data, which is then collected and analyzed, and finally can be put in some sort of a public database. And for this we use a tool called Granula, which is a tool for monitoring, modeling, archiving, and visualizing the performance of graph analytic systems. So what that means is that as a platform developer, you define some sort of a model of your system. So You could think, for example, for something like a Pregel system, you have a model which is, well, you have your complete job, which you can split into loading the graph, running the algorithm, storing the results. But then running the algorithm might be split into super steps, and each super step might be split into doing computation and sending messages, etc., etc. So this is something you can define through Granula and expose the start and end times of each phase in your logs, and Granula will then combine that with, for example, CPU monitoring, memory utilization monitoring, etc., to give you insight into what's going on inside your system during the execution of an algorithm. And I'll give an example of that later. So for benchmark compliance, we require a very simple model that's able to distinguish between processing time and overhead. So that's something that any system should be able to provide. Extended models and system monitoring are only to help benchmark, or to help system developers rather, or users to figure out the performance of their systems and to better understand where they might be losing performance. So Granula is still in a bit of a prototype stage, although we're getting quite close to getting a really functional version of it. To give a bit of an idea of what you could get out of Granula, I see the colors are a bit washed out, but it'll be fine. So this bar represents the time frame of executing a single job, and it shows that for this particular system, this job can be divided into two stages. So you load the graph and then you run an algorithm. If you then zoom in on the algorithm part, you might get something like this. It's a Pregel-like system, so you have different super steps. The first two take a lot of time and the other ones seem to be taking gradually shorter. And you can combine this with monitoring information gathered by Granula to quite clearly see, for example, that for the first super step there are a bunch of peaks in CPU utilization, and then for the second super step we see the same with kind of a weird gap. This type of information can really, as you make the model more detailed, they can really provide a lot of insight, combined with the fact that we have a broad range of applications in our benchmark. They can really give insight into where you might be having bottlenecks in your system. And we think that in addition to testing systems, we think it's our job to also help improve these systems, because ultimately that's why we're benchmarking, right? To get the best out of our systems. And the third view for the same job execution, we found, for example, that memory utilization for one system peaked at 63 gigabytes out of 64. So then we've probably found our bottleneck as to why larger graphs suddenly didn't work anymore. So this type of information is what we're trying to get at. So just to give one example of the results we got in our VLDB submission, we implemented Graphalytics on 6 different systems. So at TU Delft, we implemented the benchmark for Giraffe, GraphX, and PowerGraph, which are 3 community-driven open source systems. And the implementations for PGX, GraphMath, and OpenG were provided by Oracle, Intel, and IBM respectively. All these experiments were run on a supercomputer in the Netherlands, which we at TU Delft have access to, so we did our own auditing, let's say. One of the interesting things we found is if we look at the algorithm variety experiment, so we have 2 different graphs, a rather small one and a larger one, and then the 6 different algorithms. One of the things we found is that between these algorithms, there's quite a significant variation in the relative performance between the different platforms. So although in general you can say that In particular, PGX and GraphMath are usually the fastest. It's not as simple as saying PGX is always 2 times faster than GraphMath or vice versa. There's definitely a trade-off here, and there's no clear winner or between all of these different algorithms. So there's definitely value in looking at the algorithms that you in particular are interested in and seeing which of the platforms perform better on those. A second kind of interesting result was that for one particular algorithm, local clustering coefficient, we actually found that on this small graph, where for reference, the graph on the left is about an order of magnitude smaller in terms of number of edges than the graph that's used for the right bar of results. Local clustering coefficient was actually slower on the small graph, and it turns out that this graph was a particularly dense graph, and local clustering coefficient scales with the square of the degree of vertices, which explains why for this dense graph, it was the slower of the two. But this is the type of insight that you generally only get if you run on a number of different applications, a number of different kinds of graphs, rather than this really narrow-minded single algorithm, single data set kind of experiment. So just to wrap up with some future plans, the first draft, the first public draft of the specification is coming soon, hopefully in the next month or so, definitely before VLDB happens. There are a couple of things we still want to have a look at. We're still working on defining exactly the execution rules of the benchmark. So right now we have a bit of a verbal understanding between the partners in our task force what is and what is not allowed in the benchmark, right? To make sure that people don't game the system. But clearly this also needs to be written down and really worked out in detail in the specifications, which goes a bit hand in hand with an auditing process and defining what kind of openness there needs to be from the side of benchmark or test sponsors, as we call them, for submitting results. But after we get through with this, we'll be able to publicly share this draft with you and hopefully receive more feedback on how we can improve for the final release. Another thing that we want to do in the near future is to actually put out a results archive in public, right? So something similar to Graph 500 or Top 500, where we announce periodically, let's say, the top performers in the benchmark. But one of the key questions we still have there is how do we actually present all of these numbers? Because right now we have a bunch of different experiments, and usually these top 500 lists have some sort of a single value by which you define performance, and we don't have that yet. So we need to figure out how to go about that. And finally, we want to extend this tool chain, and in particular in the direction where Granula is heading. So one of the things we're working on is adding more detailed performance characteristics. So for example, low-level hardware counters could be included. We could include some sort of an automated bottleneck detection, right? If we have a detailed model and we have the utilization characteristics, then we might be able to identify bottlenecks automatically in your system across these different experiments. But this is all still ongoing work and not going to happen in the next week. So to wrap up, we defined Graphalytics, a benchmark for graph analytics. We've published on our experience implementing this on 6 different platforms. and the first public draft of the specification will be coming to you soon. All right, are there any questions?
So how many algorithms do you have in the bench?
We have 6 algorithms currently. They are BFS, weakly connected components. We have PageRank, local clustering coefficient. We have community detection, and in particular label propagation. And finally, for weighted graphs, we have single source shortest paths.
Are you going to add more?
There will in the future probably be more algorithms. We just need to figure out how we want to structure that, because as we add algorithms, the amount of time it takes to run the benchmark quite significantly increases. So we want to prevent this kind of bloated, let's say, set of algorithms.
More questions?
So on the performance graph picture for local clustering coefficient, giraffe and graph X are missing very reason.
Yeah, there's a tiny F here, which means that they failed. I think for both of them, actually, they ran out of memory. So they were actually hard crashes.
More questions? Okay. So thank you very much.